Well, hello guys, Mr. G here. In the last video we were learning how to calculate the net work done on an object when the object is moving on the inclined plane. Today we're going to be learning a new theorem which is called work energy theorem, and it's going to be one of the most important theorems you will learn in the grade 12. Okay, now in these theorems we are going to relate the net work to kinetic energy. Okay, now we are going to recall that net work is going to be equal to the net force multiplied by the displacement multiplied by the cosine of theta. Now in this case here that we have on the left, in this picture you have an object that is moving to the right and the net force is also to the right, therefore the displacement is to the right, and in this situation here theta is going to be equal to 0 degree and cosine of 0 degree is equal to 1. Therefore from here we have that net work is going to be equal to net force multiplied by the displacement. Okay, now previously you learned two important concepts. One of them is about net force, and you know by Newton's second law of motion that net force is going to be equal to the product of mass and acceleration. Okay, this is a very important definition, and you know by equation of motion that a final velocity square is equal to initial velocity square plus 2 times the acceleration multiplied by the displacement. If we rearrange this formula for displacement, we can have that the displacement is equal to the final velocity square minus initial velocity square divided by 2 times the acceleration. It's the same thing, it's just rearranged for to calculate displacement. Now, if we substitute these formulas in the formula of net work, we have that the net work is equal to mass multiplied by acceleration, which is the net force, multiplied by the final velocity square minus the initial velocity square divided by 2 times a. Now, if we do this one here mathematically, because this is now math, we are going to have the following: net force is equal to ma multiplied by final velocity square divided by 2a minus mass multiplied by acceleration multiplied by the initial velocity square divided by 2a. The acceleration cancel in each case, as you can see there. What do we have? We have the net work is equal to mass final velocity square divided by 2 minus mass initial velocity square divided by 2. And in grade 10 you also learned that kinetic energy is equal to half mass multiplied by the velocity of speed square. If we notice here, what we have is in actual fact the kinetic energy final and initial. Let's see what I'm saying. Net work is equal to half mass multiplied by the final speed square minus half multiplied by mass multiplied by the initial speed square. So all this one is kinetic energy and this is kinetic energy. So we have the net work is equal to, in actual fact, final kinetic energy minus initial kinetic energy. And you also learned that final minus initial, as it is there, is not other thing than the change in kinetic energy, and that my lovely people is what we say that is the work energy theorem, where the net work is equal to the change in kinetic energy. This one here is the work energy theorem. There are other ways of arriving to the same theorem, just using these working from formulas that you already know, but there are other formulas even that will get you to the same end, which is called the work energy theorem. And if we write this one in Word, it says that the net work done on an object is equal to the change in kinetic energy, and this one is the formula, the very important formula. You are going to use it all the time in this topic. Okay, now this have some limitation, not many, but it have some limitation. So this theorem can only be applied to two situations. One, when they are particles, only particles, or when they are objects, but these objects can be considered particles. And there are some particle models that we one day will speak about that, but this is the two limitations for this theorem. So you're going to be using this theorem most of the time, in other words, because in physics, when we speak about objects, we are not really speaking about objects, but we are rather speaking about particles. And then, as usual, we're going to look at one example so we can see how to apply the work energy theorem, and it's going to be the end of the video. So let's look at this example. Let's say a 6 kilogram block initially at rest is pulled to the right along a horizontal frictionless surface. There is not friction. Frictional force is equal to 0 by a constant horizontal force of 12 Newton. This is the value of the applied force. Find the speed of the block after it has moved 3 meters, and this one is the displacement is equal to 3 meters. Now, to do this work, we have to calculate the final speed. Now, what is the best way of calculating the final speed in this case? It will be by using the work energy theorem. Now, the work energy theorem, there are other ways, but we are going to focus in the main purpose of this lesson. Is equal to a net work is equal to change in kinetic energy, and I want you always to begin from there because that will give you 1 mark. Now, the rest, you can now break the kinetic energy in parts, which is half mass final speed square minus half mass initial speed square. And another important data we didn't mark, starting from rest, initially at rest. So the initial speed is equal to 0, and therefore this is equal to 0. Now, net force. Before we go to the net work, we are going to get the work done by each of the forces. So let's draw the free body diagram real fast here. Now, here is the free body diagram on this side of all the forces acting. I didn't want to show you how to do it because we've done it many times before. This is applied force, the normal, and the weight. Those are the forces acting. In the x-axis, remember this corresponds to the displacement. So net work, guys, is going to be equal to the algebraic addition of the work done by the applied force plus the work done by the normal force plus the work done by weight. You have to add algebraically the work done by each of those forces, which are the forces acting on this specific block. Guys, you know, because of the previous video, please, I'm going to leave the link so you can watch it if you did not. The work done by the normal force, and let me tell you something, is not always going to be 0. In this situation, is 0. Work normal doesn't do not do work in this situation, but it's not always going to be like that. The angle is 90 degrees. Here is 90 degrees, and therefore the cosine of 90 is 0. The work done by normal force is 0. And if you go to the weight, it's also 90 degrees, and then this one is also going to be 0. So we only related to the work done by the applied force. And if we go back here, the work done by the applied force is equal to the product of applied force displacement cosine of theta, which in this case is 0 degree. So if we substitute this side, we have the applied force is 12 newtons, the displacement was 3 meters, cosine 0 degree, and this will give you 36 joules. So now you can substitute in the network. You can substitute everything in the formula, but I prefer to be calculating step by step. So when we substitute everything we have that 36 joules is equal to half the mass of the object is 6 multiplied by the final speed to the power 2, guys, and this one is now simple math. It's 2 multiplied by 36 divided by 6 equal to VF square, and then here is just getting the final answer. So the final answer for the final speed, remember that you have to get the square root, is going to be equal to 3,46 meters per second. Guys, this is the end of this video. I just show you how to get the work energy theorem. You don't have to do any of this. The work energy theorem for you start from here. That's it, end of story, nothing to say. And then one example of how to apply. Next time we're going to do some questions related to work energy theorem, or even the network, definition of work, and so on. But this one is the end of the video. Thank you for watching. I'll see you next time. Subscribe for the channel if you think this one helped. Thumb up. I'll see you next time. Mr. G here.